Alright, we're back with part 2 of some practice problems for motion in one dimension. These videos have basically been problems that only require one equation to solve. And we've, in the last video, learned how to use these two equations right here. And so now we're going to, these problems are going to either be this equation or that equation. And we'll go ahead and work through them. So this problem states that a car starts at 5 meters per second. Alright, so I just like to start writing things down. If a car starts at 5 meters per second in math, that means that its velocity initial was 5 meters per second. And it accelerates uniformly to a speed of 10 meters per second. Well, that means that its velocity final is 10 meters per second. In that time, it traveled 20 meters. Alright, so in that time, it traveled 20 meters. That's delta x equals 20 meters. What was the time that was taken, essentially, to get from 5 meters per second to 10 meters per second and travel 20 meters? How much time did it take? And so we could start up here. This problem has acceleration in it. We don't know acceleration, so there's one unknown. We don't know time, so there's two unknowns. At two unknowns, I'm already like, yeah, let's not even try this one. And then this one down here, we've got v initial, v final, delta x, and we're looking for time, so we have one unknown, and that's time, and that's the unknown that we're looking for. All the other variables are known. All right, so we can go ahead and plug in what we know, which is that delta x equals 20 meters. 20 meters equals v initial plus v final. Well, v initial is 5 meters per second plus v final is 10 meters per second. Divide 2 times t, right? That's the equation. All right, so 5 meters per second plus 10 meters per second, 15 meters per second. Divide by 2 is 7.5 meters per second. So 20 meters equals 7.5 meters per second times time. Well, now we're going to use some algebra to get t all on its own. We're going to divide both sides by 7.5 meters per second. 7.5 meters per second. Alright, so what we know now is that time equals 20 meters divided by 7.5 meters per second. And so we're going to go ahead and invert multiply, right? As far as the units go, we're going to go ahead and divide 20 by 7.5. 20 divided 7.5 gives us approximately 2.67. And then the units inverting and multiplying are going to be meter seconds per meter, right? Because we inverse multiply. The seconds ends up on top, multiplies with the meters, and the meters ends up on bottom. And so the meters cancel, and we end up with 2.67 seconds, which is good. We're looking for time. The dimensional analysis says we probably did this one right. Another thing that you're probably going to get an intuition for is whether an answer sounds reasonable. So the dimensional analysis works, but does 2.67 seconds really sound like a reasonable amount of time? To go from 5 meters per second to 10 meters per second over the course of 20 meters in distance. To me, it looks pretty reasonable. It's not huge, it's not too small. Obviously, we don't know what kind of car it is. And so, in the US, we tend to think of things in miles per hour, so meters per second doesn't always register for me. But I would say 2.67, I mean, it looks like a reasonable amount of time. I mean, firstly, it's positive. That's always nice. Positive times are good. If you get a negative time, it doesn't necessarily mean that it's wrong, but you probably missed a multiplication by a negative. It's probably wrong. So if you get a negative time, we don't like negative times in physics. We're always looking for the positive times. And so always be aware of that. So that's this problem. That's how we walk through it. Alright, and now we've got one more equation to learn how to use. Of course, once you know one of them, you kind of know all of them. They're all very plug and chug once you figure out what all the variables are. So this one says a train was initially measured to have a velocity of 10 meters per second. So V initial equals 10 meters per second. It began to brake and came to a stop 5 seconds later. So time was 5 seconds. Alright, time equals 5 seconds. What was the train's acceleration? Alright, so this is an interesting question. Because for the first time in the problems we've done, we started at a higher velocity than we ended at. Well, let's see, a train at a velocity began to brake, became to stop 5 seconds later. Oh, I forgot to add one thing to this problem. Oh, no, I did not. Alright, so what would our final be? We start at 10 meters per second, and it came to a stop. Alright, so it comes to a stop after 5 seconds. Starting at rest usually indicates a 0 initial velocity. Coming to a stop usually indicates a 0 meter per second final velocity. So we have V initial, V final, and T. And for the first time we started at a higher velocity than we ended at from all the practice problems that we've done. And so when I call this acceleration, it's kind of a blanket, it's an overarching term. But really, when you slow down, we tend to call that decelerate. So really what we're looking for is deceleration. But you're probably going to see it, you're probably going to be asked for acceleration. I don't know whether deceleration is going to show up in the homework problems very often. So anyways, I mean, we've covered these three equations, so we really know which one we're going to use. But I would recommend that you take a look at these and see why these three equations aren't the best fit, and why this one is. So, V initial, we have it. V final, we have it. Time, we have it. And we're looking for acceleration, that's our one unknown. And so we have 3 knowns, 1 unknown. And for that reason, we're going to use it, because we're only going to need to use one equation here, just this equation. Alright, so acceleration times time, which it took 5 seconds, plus V initial, which we extrapolated from the problem was 10 meters per second, equals V final, which from the problem it came to a stop. That means 0 meters per second is V final. Alright, so what we can do is we can subtract 10 meters per second on both sides. Minus 10 meters per second. Subtract it from both sides. 0 meters per second minus 10 meters per second is minus 10 meters per second. And that's equal to acceleration times 5 seconds. Alright, so now we want to get acceleration alone, so we're going to divide both sides by 5 seconds. 5 seconds. Alright, cancels here to 1. And so we find that acceleration equals, well, minus 10 divide 5. Minus 10 divide 5. I shouldn't have to plug that in. It's clearly minus 2. Alright, minus 2. And then, so remember we're going to invert and multiply the units, so seconds will end up on the bottom, and we'll end up with units of meters per second squared, which is fantastic because of the dimensional analysis we know that acceleration is supposed to be in meters per second squared. So the fact that it turned out that way is really good. And also it's a negative number, which we were expecting, right? Because we started faster than we ended. And so really we were decelerating. Deceleration is defined as a negative acceleration. So this seems like a reasonable answer. And that concludes just kind of going through these two videos and trying to find which equations to use that are most effective. Next video I'm going to make, we're going to have to use multiple equations to solve. Alright, I hope this was helpful, and I'll see you next video.